All right, very good. Yeah, this seems to be working. Thank you very much, Antoine, for the introduction. So we've already had one lecture last week. I see some new faces in the audience, so there's and I was expecting this, so there's going to be a couple of slides where I'll just try to make a couple of points that I already made. And this is actually going to be a fun lecture. It's a topic that is a little bit aside from the ultra-fast spectroscopy set of things that people do, and so in a sense it's a little bit useless, but in another sense is a lot of fun. And so the purpose of this lecture is to make sure that Antoine neither checks emails nor falls asleep, which is usually what he does when I talk about this. And I'll try to. So the purpose. I seem to be the only person that is very interested in this, and so my goal is to get you also interested in this. Okay, so let me repeat a couple of things that I said the last time. All right, so there's a lot of talk about quantum materials. Quantum materials are, people talk about quantum materials in very loose ways. They usually refer to strongly correlated electron systems or many of these systems. And last time I gave my own view of what a quantum material is, and we will keep it as an operational definition. So in my book, a quantum material is a solid which has some macroscopic behavior that we cannot understand even qualitatively using classical physics, in the sense that even a very difficult metal-insulator transition can be described, maybe making wrong statements, at least qualitatively, thinking about classical physics and thinking about classical electrons that are either more or less localized. But there's other phenomena that cannot be understood by thinking about classical particles, and this would be my definition of a quantum material. And of course, a prominent example of a quantum material is a high TC superconductor that I'm sure all of you have heard about. So these are these doped oxides of copper. So they're sort of rusts of copper that we've learned how to grow really, really well. And what they do is that although these are ceramics that have very bad conductivity, below temperatures that actually go from all the way to almost 200 Kelvin in under pressure in some of these, so 2/3 of room temperature, effectively. These materials exhibit a zero resistance state, which is so they have perfect conductivity, like an electron in vacuum, but they also display the Meissner effect, which is the most remarkable phenomenon of a superconductor in which a magnetic field is fully expelled. And there's of course a lot of work that has been done to understand these phenomena in the classical superconductivity materials, superconducting materials such as some metals and what we understand as BCS superconductors. But very little or very much is known about how these materials work. And there's lots of people that have got lots of theories of how these materials work, except that the theories of these different people don't match with one another. And so we believe that we don't understand how high TC works based on this effect, but based on this. So what we in our group and what my sort of research interest is about using light typically, but doesn't have to be light, and understand how these complex materials that exhibit quantum order, say, that have by and large been studied almost exclusively in linear response. So people use weak probes to study small perturbations to try to understand how these materials work. So we're interested in using excitation, which is slightly stronger, and explore the nonlinear response of these materials, of their collective modes. And we do this generally using light. So there's at least two goals, broadly defined. The goal number one is to reveal new functionalities that may be hidden because they don't appear if one doesn't do a special thing, but also to create, to manipulate the properties of these materials that emerge because the light or whichever stimulation we're applying to this has a large energy compared to the Hamiltonian energy scales that determine the collective properties of the system. So we don't necessarily use probes, but we use pumps, where a pump is something that has an energy that is comparable to the microscopic energies of the system, whereas a probe is something that is small and that only probes the system. And we also want to understand how these phenomena occur at high speed, and this may be interesting for device applications. So a lot of the work that is usually done in quantum materials has got to do with properties that occur at very, very low energies. And this is because when a condensed matter physicist wants to understand something, they tend to cool things down as low as they can and try to make things slower and slower and slower. And this is, of course, very nice. There's a lot of, it helps us to think lucidly about these systems, to use statistical mechanics, etc. But sometimes, if one wants to apply these materials to be incorporated in high-speed devices, one needs to go away from this obsession with making things slower and slower, and one needs to understand non-equilibrium properties of these systems. Okay, so these are sort of very broadly, very, very broadly defined ideas about what we're interested in. Let's see. If you take a solid, of course, a solid of any type has a continuum of excitations that goes from 0 frequency to many very, very high frequencies. But let's consider the bound electrons. So let's think something that goes from very low frequencies to a few eV energies. So there's of course electronic excitations between bands, for example, at energies of EVs. This is something that has been, when one considers nonlinear light-matter interaction, has been explored extensively by a lot of groups, primarily because it's easy and because one buys lasers and one has a laser that emits light at 1 EV or 2 EV. And so that's something that there's lots of problems already, and one hasn't, one perhaps hasn't worked enough on trying to change this effect. So these are the excitations that happen at these energies. There's a broad mid-infrared region, so in the 10 to 100 milliV energy scale, which means, well, let's see, between 100 Kelvinish and 1,000 or 2,000 Kelvin energy temperatures. And this is where phonons are. There's a lot of work that one can do in driving phonons non-linearly rather than just probing them. And this will be actually the topic of my lecture in 2 weeks from now. And then there's low frequencies, say at 1 millieV, for sake of argument, 250 gigahertz. And this is where collective phenomena dominate the electrodynamics of the system. Okay, and so this is a Mexican hat potential, and I won't belabor this too much. But the topic of today is going to be about taking a superconductor, specifically a high-temperature cuprate superconductor, and understand how this high-temperature cuprate superconductor responds to stimulation on these energy scales around 1 terahertz when the field is strong and when the material is being perturbed. So there's actually, I'm only going to talk about one thing today, and I'm probably going to have time to tell you. I'm probably going to have time to talk to you about 2 topics. One, there's many other things that we do, and depending at the end, I may just list a couple of things, maybe opening up some discussions later on, or maybe I'll go into a little more detail about this. Okay, let's see. So this is the one incarnation of a phase diagram of a cuprate superconductor, which is again this material. This was in some news and views written by 2 theoretical physicists, Steve Kivelson and Eduardo Fradkin, a couple of years ago. The most important thing that you need to take away from this is that in the phase diagram of these cuprates, there's a lot of complexity that takes place with a lot of very interesting forms of self-organization. Some are more zoological and not very fundamental. Some may be important for the working of these superconductors. But the most important thing is that below this temperature, regardless of who one gets into this, the system acquires this collective order, which is the superconducting state. And if one looks at low energies, which means at relatively low frequencies and on relatively long length scales, the behavior of these very complex systems is rather universal. So this is one of the beauties of superconductivity, that regardless how hard or how difficult it is to understand how you got in there, then once you have it, you have a lot of things that happen that can be understood on very simple basis. And this is the topic of today, is to try to understand how, at low energies, there's plasma waves that are optical waves that are excited by a light field that live between the layers of superconductors that can be understood by very, very, very simple considerations. And you'll see how by maybe using one fudge factor, which could be a dielectric constant that we just make up to fit the data, we can describe reasonably well the nonlinear physics of these cuprates. Okay, let's see. Let's think about the electrodynamics of one cuprate. So there's this layer. Let's say one important thing that you need to, if you don't work on cuprates, the only important thing that you need to start from is that one thing, okay, well, this is just as bad as the other one, that one can think of these cuprates as layered compounds. Well, they are layered compounds, but one can think of layers of copper oxygen planes, and then which are separated by other stuff, which are charge reservoirs that are used to change the doping on the layers. Superconductivity appears to develop most strongly in the layers through some mechanism that is going to be dominated by things that happen in the layers, a little bit coupling to the outside. And then this superconductivity is made three-dimensional by tunneling through these non-superconducting regions and by making superconductivity three-dimensional. Okay? And here I've depicted the way to think about an order parameter. So I have this complex wave function with a modulus, which is the length of this vector, and this number is proportional to how dense the superfluid is, or how many Cooper pairs I have in there, or how much of a field, of a magnetic field, I need to apply so that this thing breaks. Okay, this is depicted in this. And then there's a phase, which we depict as this angle, and these are two excitations. This is a well-known Mexican hat type description of this order, and so there's two modes of this that are described by this in this surface. One is the excitations of the modulus. So this is by analogy usually discussed in terms of the Higgs mode of the solid, and then there's phase excitations, which are thought of as a Goldstone mode of this state. Let's see. So how does the superconductor respond to electromagnetic radiation? Let's apply an electric field in the plane first of these cuprates, and let's look how when the field is small, in principle, in first instance, how does the superfluid respond? So we can start, the easiest way to think about this at low frequencies are starting from London equations, which I'm just going to throw here. So the London equations tell you that if you don't consider these excitations at high energies, which is where the paths are being broken, these are excitations that destroy the order. At low frequencies, effectively, I can think of these excitations as those of an inductor. So I have a real part of the optical conductivity, which is zero everywhere except at zero frequency, where I have a delta function, which is where the perfect conduction takes place. And then I have an imaginary part, which is the inductive response of the system, or the response that is pi half out of phase with the current, which diverges as the frequency gets smaller, as in this way, and it diverges with a strength that depends on the density of the superfluid, which is the length of the vector that I showed to you. Another way to see this is that there is an inductor, L, which let's see, J omega L, which is the inverse of this, right? So, and L is equal to m star divided ns e squared, okay? And this is going to be pretty important later. So think about this inductive coupling, which, okay, so I can transform these London equations, and instead of calculating the relationship between the electric field and the current, I can depict those as the relationship between the electric field and the displacement vector, and if I go through the math, I can tell you what the optical properties of a superfluid are, epsilon, the dielectric permittivity. So the dissipative part, which now for various reasons is considered the imaginary, not the real part, has a delta function of 0 frequency. And importantly, epsilon 1, this is assuming that epsilon infinity doesn't exist. This is the only thing that exists here. This is the way epsilon 1 looks like. So, which tells me that epsilon 1 will be negative for all frequencies below some number that depends, some frequency that depends on the square root of the superfluid density, and it will be positive after this, which means that in reflectivity, I will have a reflectance, so the modulus of the reflectance, which is 1 for all frequencies below this number, and then will go to 0 when this epsilon 1 gets to 1. So depending how steep this is, I will have this edge being more or less smeared. Okay, this is really first year optics. The most important thing is that if I try to look for these features in the plane of superconductors, I won't find very much, because what I have on top of this are also the normal electrons of the system. Remember, in a superconductor, you only have very few electrons that condense close to the Fermi surface, and have all sorts of other electrons kicking around. And so these other electrons, which are depicted in yellow here, will have a much higher density. As I said, the plasma frequency, the 0 crossing of epsilon 1. So they will have, in the limit of very low damping, they will have a very similar epsilon as the superfluid that I told you about. But the density will be far higher. Say it's 100 times higher. It's 10 to the 23 instead of being 10 to the 21 per cubic centimeter. So the plasma frequency will be 10 times higher. And hence, if I add all the epsilons, the reflectivity will be dominated by this. Another way to say this is that the quasi-particle, not the electrons will screen whichever response the superfluid wants to give. So this is data taken from the PhD thesis of, I think, of my postdoc Daniele Nicoletti, who measured in BISCO. In this type of superconductor, measured the in-plane optical properties. And as you can see, there's a signature probably of the superconducting gap, although here at about 40 milli-V. But then the plasma edge that dominates the response is really that of the electrons. And there is no clear signature in the plane for the superconducting order parameter. Okay, so this is a fact of life that you know, people cannot measure these in-plane properties very clearly. The situation, however, is very different if I look out of plane. In most of these cuprates, especially in the underdoped region, the out of plane properties still have a response which is given by which is very similar, you know, is similar to the one I told you about. The only difference is that the effective superfluid density, because of the tunneling, is reduced compared to the superfluid density that I have in the planes. What this means is that this is a weaker superconductor. It's an anisotropic superconductor, and if I try to measure the current at which the superconductor ceases to be a superconductor, the critical current, this will be different out of plane as opposed to in the plane. So all the critical parameters, such as magnetic field, etc., will be different. But I will still have the response of a superfluid. And I will have a plasma frequency that will be anywhere between, say, 100 gigahertz to 10 terahertz, depending on the details. On the other hand, the quasi-particles, which are the yellow thing that used to screen my response in the plane, will actually not transport very well. These materials are insulating or almost insulating perpendicular to the planes. Let's say that the effective mass of these electrons is very high, and hence the 0 crossing of epsilon 1 is to the left than the 0 crossing of the one of the superfluid. So the superfluid edge will come to me in its full glory, and I'll be able to see this. And people have done a lot of work, and now all of a sudden I have a very clear effect that I can see in the optical properties perpendicular to the plane that is directly related to the strength of the superfluid. Modulo some parameters, which are effectively sort of chemistry or materials parameters, which have got to do with how far away the planes are, what exactly is the electric constant of the stuff in between, what is the capacitance of the planes, etc., etc. But given these parameters, and if, let's say, if I change temperature, the position of this edge in reflectivity, which is now this edge measured in the reflectivity of an optimally doped cuprate, lanthanum-strontium cuprate, which in this case is at 2 terahertz, the position of this edge will be proportional to the density of the superfluid perpendicular to the planes. Okay? And above TC, this edge will go away. One easy way to see why I have an edge below TC and I don't have an edge above TC is thinking that below TC I have tunneling, so effectively tunneling that shorts all the quasi-particles, all the electrons, or the quasi-particles. And so effectively I can think of this low-frequency electrodynamics as that dominated by an LC circuit, which means that if I put an imbalance in Cooper pairs going from this plane to this plane, this thing will ring because I will have inductively capacitively coupled planes. And this defines the plasma resonance in as much as L is a quantity that depends on the density of the superfluid. Okay? And so square root of 1 over L omega C will be something that carries information, carries boring information about the capacitance and very interesting information from the inductor. If I go above TC, this inductor becomes infinity because remember n was at the denominator, so it goes to 0. And so I will be stuck with an RC type response, which is damped in time and relatively flat in frequency. Okay, so this is why in a sort of very a simple picture this is one way to think. Yeah, oh yeah, I'm sorry, yes, sure.
Do you see, okay, could you comment on the fact that in the plane, do you see the pseudo gap and in reflectivity?
Of course you can see all the, okay, I am restricting myself in this context to the dynamics at frequencies that are far below the gap excitations. Of course, you do see the gap. Okay, you do see the superconducting gap already in reflectivity, and of course you'll see that very clearly in sigma 1. You will see the pseudo gap above, but then there's a whole different story. There you'll be studying in linear response the excitations of the system, or in nonlinear response, the excitations of the system. But these are energies that are far above the ones that I'm discussing. Okay? So what I'm thinking of now are excitations. These are 20 millieV. So what is 20 millieV is 5 terahertz. Half a terahertz or 1 terahertz are 4 millieV, so it's down here. Everything I'm going to tell you about today happens out of plane at this energy. Yeah, these are the electrons.
And where is the pseudo gap?
The pseudo gap.
Yeah.
You don't see it very clearly in reflectivity. Okay. You'd have to look at sigma 1 and sigma 2, but you see the superconducting gap reasonably clearly already in reflectivity. Okay. Yeah. So. Okay. Now we want to understand this a little bit better, and let's think about how to think about this tunneling of the perpendicular to the planes. So let's start. So the tunneling perpendicular to the planes has been discussed in terms of a Josephson type phenomenon, although actually until very recently there was rather limited evidence that this was really dictated by the Josephson effect. This is going to be part of what I'm going to try to convince you of. But let's think of tunneling perpendicular to the planes as follows. So I can think of a current. If I apply, what am I going to say? If I apply I can start thinking about the phase of these order parameters, which doesn't have to be, would like to be 0, because this minimizes the energy, but let's say there's a finite phase difference between the planes. And what I know is that if there is a finite phase difference between the planes, I will have a current that follows the sign of this phase difference, and through a proportionality constant, which is related to the superfluid density. Okay, which is the critical current. And the second Josephson equation tells me that this phase can be made time dependent from outside by applying a voltage. What this tells me is that the phase changes in time proportional to the integral, the time integral of this voltage, which is effectively the vector potential of the field, okay? Whereas there will be a finite phase if I apply a static magnetic field, okay? So, and if I now take these things, and again, in the spirit of the LC circuit that I told you about, I can work out what the equivalent impedance is coming from these equations. And I can tell you that there is this okay, C I told you that there was, and that there is this inductance that can be calculated to be a number that for small phases is equal to h bar divided 2e IC, okay? And on the other hand, this inductance will depend also on the inverse of the cosine of the phase difference between the planes. So you will see that this diverges, for example, when the phase is either pi half or 3 pi halves, okay? And now so I have a frequency that depends on two numbers. The length of, if you remember my clock, the length of the clock, I don't know what the lancette, what is it in English, I forget, of the little thing is, the length is IC, and phi is the phase, okay? So if let me repeat what I said. If phi is a small number, which is what I see in linear response when I look for this edge, I have an LC circuit at a frequency, so now L is a small number, is the smallest. It's much larger, is much smaller than the resistance that comes from the electrons that are still there. And so I'll have this LC circuit, and the frequency of this will be dependent effectively only on the density of the superfluid and not on the phase, okay? 1 over square root of LC. And so this is what happens, for example, when I do an experiment either with a spectrophotometer or with those of you that have been at my lecture the last time, I told you about how we measure spectra. What we do, for example, is we use a light field, which is in the terahertz range, which is, say, half cycle or 1 cycle, which is very broadband. And then we measure it before and after it interacts with the sample with sensitivity to both the amplitude and its phase. In this way, we can extract both real and imaginary part of the optical properties. And this is what you see in linear response. If you shine one such pulse and you look at the way, and you look at its reflection coming out, you see all this ringing in the wake of the pulse, of the reflected pulse below TC. These are Cooper pairs that are going up and down from the layers, and they ring at the frequency which is given by the plasma frequency. Okay, so this is something where you can get all sigma 1 and sigma 2. So this is actually a relatively straightforward, within reason, relatively straightforward measurements, and this is just to tell you that in reality, when you measure these optical properties perpendicular to the planes, you will see the black curve will be above TC, which is for this specific compound, is say 40 or 50 Kelvin. You will see that above TC, the reflectivity is flat, whereas it has an edge below TC at about 2 terahertz, whatever, 1.8 terahertz. The epsilon, the real part, sorry, the dielectric constant is flat at all frequencies except way back there at finite frequency, at 0 frequency, where you'll see a delta function. Whereas the real part is negative and it crosses 0 at this point. And again, in the conductivity, I will have a real part with a delta function at 0 frequency and an imaginary part that diverges. And it becomes infinity at 0 frequency with the Meissner effectives. Okay? So this is really what you can measure in a typical pump probe experiment if you only use the probe. You do this. Okay? So this is now the response. This has been known for 20 years. Because you can measure this with a spectrophotometer and you don't need to use these pulses, except that there's a certain satisfaction to see the Cooper pairs go up and down in time. Now let's think about when the phase is a finite number. Of course, this inductor becomes larger, and maybe it becomes at some random phase it'll be of order the resistance, and then I'll have a more complicated response. But exactly when the phase is pi half, okay, when the phase is pi half, what I will have will be a pi half junction, which means that through all these points, the Josephson junction or the layers will be uncoupled by tunneling, and only the resistance will control the flow of charge of normal electrons. And when the phase, right, inductive couple, I'm repeating the point. So this is now will be opened, this tunneling will be open, and I will only have this conduction. And when the phase is pi, what I will have is a negative inductance, which means that if I apply a field like so, the current will go like so and vice versa. But effectively, I will have pi shift, a pi shift in the response, but it will look like the phase beam equals 0. Right, this is what I said. Here, I'm shorted again, and I have this negative inductance. Okay, so if I now apply, I remember I told you, the phase advances in time with the integral of a voltage drop, which means that if I apply a voltage, what I should see is an oscillation which occurs at a frequency that depends on all the parameters of this, but it will also depend on how big the voltage is that I'm applying. Okay, so I've made a little bit of a long story. What I've just explained to you is the AC Josephson effect, which we learn in school. Okay, so this is which, by the way, when people discovered the appearance of an edge in the spectra in say late 80s, early 90s, in the spectra perpendicular to the planes, it took a while before people really saw this as being related to the Josephson effect. People thought it was the gap, and who knows. And then only with this paper, I think there was actually maybe earlier papers that indicated this, but there's this paper where they clearly showed this, where they clearly showed that if they grew a bisco crystal and they could apply in the right fabrication, they could apply a DC field and observe terahertz radiation by applying a DC field. Okay, so this is a very nice paper which shows that you can have a DC to AC converter. Of course, the IV curve doesn't look as nice as the AC Josephson effect that I showed you, because these are many, many layers. Everything I've told you about are predicated on just having one single layer. And so you need to synchronize these planes, and there's a lot of just messy nonlinear physics that takes place, and this technology never quite took off in a sense of becoming a practical source. But of course, this is very attractive in terms of having a high frequency device that is based on high TC cube rates. Okay, right. So for this, but for many other reasons actually that I won't go into too much, what we started working on a few years ago was the following question: can I use a strong field and flip this phase at very high speeds? What I would like to do is flip this phase at a speed that is high compared to all other fluctuations and control it at fast rates. If only because this is something where I can make a switch which is based on a superconductor. I can make an ultra-fast switch, and I can control it in new ways. And just because this seemed like a lot of fun, okay? So to do this, what one needs to do is to have, if you calculate the phase, as I told you, the frequency with which the phase flips is proportional to the peak, to the voltage. Okay, so if you now apply a DC voltage or a quasi-DC voltage, how big of a voltage do I need to apply so that I have a pi half or pi rotation in about 1 picosecond? And if you do the math, throwing in some numbers that you just make up, you have something of order 100 kilovolt per centimeter. This was something that until a couple of years ago was not possible in half-cycle picosecond pulses, and this was part of what was discussed in the last lecture, where new developments in technology and in the use of nonlinear optical crystals has made it possible to generate pulses that are easily all the way to a few megavolt per centimeters, with which that's why we want to have these pulses, because you can do interesting transport things without exploding everything at fast rates. Okay, and I won't tell you anything about how these pulses are achieved, but it's really a very beautiful thing that now a lot of people do actually. And you can now generate a pulse like so with 100 kilovolts or 500 kilovolts per centimeter fields that lasts a picosecond or two. Okay, so first experiment that I'm going to tell you, and I'm going to keep somewhat the same pace, hopefully to make it accessible. So we start, and what we take one of these cuprates, doesn't matter which has a frequency at around a plasma frequency at around 2 terahertz below TC, and we apply a pump pulse, which is this pump pulse, in this region. So this is where epsilon is negative, which means that the excitation is an evanescent wave. For various reasons, We don't want to get into a situation in which you have to understand exactly how this nonlinear pulse, at least not yet, how this nonlinear pulse is propagating into the material, and et cetera, et cetera. So let's think about a pump at something that is far less than this, which in this case is about 500 gigahertz. And then we use a probe pulse to measure the optical property. So let's show you probe alone. I've already shown you this. Probe, imaginary part of the conductivity. So the two quantities that I'm going to discuss here are the conductivity, which when it's superconducting means it's as a diverging imaginary part, and a flat real part, and the reflectivity, which drops at the plasma frequency. This is the probe. And then I'm going to apply a pump, which is this quasi-DC field, and I'm going to look at how this plasma frequency goes backwards and forwards, if it does, and how the divergence, okay, so I start from a state in which my probe, either probe alone or probe at negative time delays, probes a divergent imaginary part of the conductivity and a flat real part of the conductivity, and then I wait in time, and I look at how these two numbers evolve in time as the field is being applied. So this is what I see. This is the real part of the conductivity. These are negative time delays. This was negative. Sorry, this was 0. Whereas the imaginary part was diverging towards 0 frequencies. That's why it's red and it's blue here. And then the pulse comes. And one of the most remarkable things that we observed was that the system went from, this is, let's see, which one is tau 1? So yeah, tau 1, this is real part. Okay, I think these are wrong. But at negative time delays, be as it may, the real part of the conductivity is flat and the imaginary part is diverging. At a given time delay, the real part of the conductivity starts shooting up, like in a metal, whereas the imaginary part of the conductivity comes down, like in a metal. And you say, okay, fine, you've broken the superconductor, good for you. But then you wait another 100 femtoseconds, and this thing becomes superconducting again, and insulating again, and superconducting again, and insulating again. So this is an example in which you can oscillate between a resistive and superconductive interlayer coupling between the planes at ultra high speeds. Okay, so this is the same thing as the AC Josephson effect, but it's, and I'm going to substantiate this more, but it's 4 orders of magnitude faster, and it occurs, and it's bidirectional, which is something that you can never do in optics, etc. So what you can do now to substantiate this is to take, remember that I told you that the 1 over omega-ness of the imaginary part of the conductivity is proportional to the density of the superfluid or to the phase stiffness. Okay, so I can take this number, which I can say omega times this curve, which will be a constant, and I can plot this as a function of time as I go up and down here. And what you see is how really the superfluid, this is the number I'm plotting, limit for omega that goes to 0 of omega sigma 2, which is a measure of the superfluid density. And I can see that it starts finite. It moves around a little bit at the beginning when the pulse starts. Then it goes all the way to 0, up, all the way to 0, up, and back. And this can be fitted by taking the experimental pulse, taking its integral. Remember, this goes with a vector potential. The experimental pump pulse, taking its integral and fudging its height. So I only have one free parameter, which is this height, which has got to do with the coupling of this terahertz field. And I can fit reasonably well these oscillations, showing that you have the AC Josephson effect in a cuprate. Remember, what I told you is that given a voltage, there was a given frequency. But if I change the voltage, if I made the voltage lower, the frequency should go down. And if they made the voltage higher, the frequency should go up. And so when Andreas, my student, did this experiment, he showed that if you plot the oscillation frequency as a function of electric field strength of the pump, you have a region below some critical field where nothing really changes. And then at some point you have this linear acceleration of the oscillation. So this is really the AC Josephson effect at ultra high rates in this compound. The other very nice, okay, great. So this is very interesting, I think, for devices and for making things. The other thing that I find rather more interesting for fundamental studies is that if you do the same experiment and you now apply the field in the plane and you probe perpendicular to the planes and you do the same thing, these are the optical properties in the plane, nothing happens. The system was superconducting, it stays superconducting. So what this experiment shows is that by using terahertz pulses, you can have an oscillating dimensionality. You can oscillate between a 1D and a 2D superconductor, and we haven't really pursued this very much, but I think that there's very interesting things that one can think about in terms of probing. One of the things, for example, that we can do is when this thing is shut off, I'm happy to discuss this later, but I wanted to move on, is that once this thing is shut off, because the phase goes through pi half or 3 pi halves, you can look at the Drude parameters of the bare quasi-particles at low temperatures, and I can tell you what their density is or what they're up to. And this is done by effectively opening up the circuit, opening up the inductive coupling and blocking the screening. So this is reasonably interesting, I think. Second, yes, Antoine.
So what your pulse has done is to induce the AC Josephson oscillations between layers.
Between layers of the cuprates. So this is a textbook demonstration that the Josephson coupling is in fact the Josephson coupling. And everybody says we knew it already, but yeah.
But what you showed is that at large field, can you go back to the
Yeah.
field dynamics?
Yeah.
So something happens at
No, this at large fields, this is what you want. Remember the AC Josephson, okay, let me remind you of the AC Josephson effect. If the field is small, nothing happens because you need to start having some voltage drop. Only above a critical field, you start having these oscillations. So, and that's the signal. This is just the fact. This low frequency is effectively following the shape of my pump pulse. So this is, it would be 0 if I was applying a DC field, but probably then I would drift. Now, the important thing is that if you try to do this in a cuprate with a DC field, you're gonna, this thing is gonna melt really fast. So, because you cannot apply several hundred kilovolt per, what is this? 100 kilovolt per centimeter fields for a long time in a cuprate because this will break. Okay. Yes, sure.
Can you induce or plug in the parameters like the coupling between of the two Josephson
Yeah.
and the distance between the planes? So
Yes.
do you get that from the frequencies of oscillations?
Okay. There is only one free parameter in the fit, and that's probably eaten away by the uncertainty that you have of how effectively your field is coupling to the, so I don't really know what my voltage drop is at that frequency exactly. So, but there is only one fit, so the answer is no, because I can fit the data beautifully just by putting one number in there. So, but in principle, I already know these numbers from the linear response. So, I mean, all the spectroscopic value of this was already evident from the linear probe. This is more of a performative thing where I manipulate cuprates in a different way. So, right, okay. Second part of this thing, and then I'm done, depending on the time, or I can tell you more. I'm going to show you another example, which I think is again another thing that I'm not really sure. It's very interesting, but it's very interesting to me. So I'm going to tell you about that. So this is when I was pumping below the edge, and now I'm going to tell you what happens if I pump exactly at the edge. In this case, what I'm applying are the phase is winding up by its own devices in a way that depends on the frequency, on the voltage. When I drive this thing nonlinearly, then the situation gets a bit more complicated. So, okay, I'm going to walk you through some maths again, but we've done the Josephson equation. So, okay, so this is my inductor, which depends on the cosine of the phase. This is my applied field between the layers, which now the field goes at the Josephson plasma frequency. It's not some random terahertz frequency. It's at the natural oscillation frequency of the planes. And the phase, remember, between two layers, because of the second Josephson equation, goes with the integral of the field. So I'll have a field sine and the other one cosine. We can swap those. But let's say that now I have a phase. Now let's forget the field and let's think about a phase, which has got an amplitude, which would be a small number if the field is very small. But can be a large number, becomes nonlinear as soon as this guy is, say, pi divided by 4 or pi divided by 5 times cosine omega jp, so the natural frequency in time. Okay, let's walk through the math. What happens is now that, remember, what I have is what I have is that the inductor, which means the eigenfrequency, which means the oscillator strength, which means the superfluid density, is being modulated at this frequency. No, sorry, the phase is being modulated at this frequency. So the oscillator strength, or the square of the plasma frequency, is modulated at this rate, which is omega p squared times the cosine. Remember, this is because the plasma frequency is 1 over square root of LC. The cosine of the cosine, which is the way I was driving my phase. Is this clear? Because I kind of got stuck. Okay, so I'm driving the phase. Which feeds back into the inductive strength, which feeds back into the eigenfrequency. Okay, trivial, but this is kind of the whole part of the talk. Which if theta is a number that is not infinity, it's now not even pi half. I expand to this. So what I have is that if theta is small, the plasma frequency remains the plasma frequency. And then if theta is a bit bigger, then it's displaced by this number, and then starts oscillating at 2 omega. So what I have is that the superfluid density goes backwards and forwards at 2 omega, where omega is the driver. Okay, that's great. Is that interesting? Okay, let me repeat this. In linear response, I'm being a little pedantic here, but I just want to make sure that this comes across. In linear response, I have the phase that oscillates at omega, and now these are my order parameters as a function of time, and they go chuk, 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 but their size, which is the superfluid density, doesn't change. When I'm in the nonlinear regime, because of this term, what I have is that the phase goes at omega, but the oscillator strength, which is the size of my watch, goes, breathes at twice the frequency at 2 omega. Okay? Good. And this can be validated experimentally if you probe, after you excite the mode, some parameter that I'm not going to tell you how I probe, which is proportional to the superfluid density. It's the integrated spectral weight at all frequencies, and I probe it as a function of time. And you can see that I'm pumping at 500 gigahertz. This is LBCO. And what I see is that I see oscillations of the superfluid density at twice the frequency, which is about 1 terahertz. And this is theory that I haven't told you how I'm doing, because I don't think we'll have time for this. And this is the experiment. Okay, so you see the experiment goes exactly at twice the frequency. Great. Is this interesting? The reason why this is interesting is that think about an oscillator in which its eigenfrequency is being modulated at twice the frequency of the oscillator. This is the sort of the very simple case of a parametric amplifier. This is a child on a swing that raises up and down at twice the frequency every time I'm on this side and on that side. And this allows me to amplify this. So that's interesting enough. Another way to say this, but you got the point. I mean, you can map what was the Sine-Gordon equation that I haven't told you anything about into a Mathieu equation in which this parametric wave with these superconducting waves, which are actually the superconducting fluctuations of the system, are being amplified in time. Okay, and because this is a parametric amplification situation, depending on the phase between the driving wave and the fluctuation itself, I can either amplify or de-amplify. This is, again, very basic Mathieu equation physics. And so this is actually very beautiful. I'm measuring here. These are the Cooper pairs ringing. So this is the spectrum measured with a terahertz probe in the time domain at 2 different time delays. What I can see is that these parametric, these plasma, these superconducting fluctuations can either be amplified at some time delays, or they can be de-amplified at other time delays. Okay? And this is captured very clearly if I plot the loss function of the system. So for those of you that are not familiar with optics, the way I think of the way light couples with a material is by plotting the inverse of the dielectric constant. And this is because this number peaks, this quantity peaks at where epsilon typically crosses 0. So this is where coupling is strongest. And this is called the loss function because this is a quantity that is in analogy with what people see when they do electron energy loss spectroscopy. So all the terminology that was used to describe electron energy loss spectra is now being taken because there's a formal similarity between the inverse of epsilon and the loss function. between the inverse of epsilon and the loss function in Eel's experiments. The most important thing is that this quantity is negative in a passive medium, which absorbs radiation. But if I build a laser amplifier, this quantity will be negative, which means that epsilon, the derivative of epsilon, this guy will not go upwards, but it will have some sort of S. Okay? So the fact that mu, another way to say this is that the skin depth of the material becomes negative, or the absorption coefficient, the thing that goes into Bayer's law, goes from negative to positive. And this, if you plot the loss function as a function of time, where red is negative and blue is positive, so blue is normal, is what I have normally. I have a very large amplification at twice the frequency of the oscillation. So this is actually very nice. And one can show that you can now parametrically amplify these superconducting fluctuations, okay? And I'm not really sure, we haven't thought very carefully yet about what one should be doing with this, amplification, but I think that there's a lot of very interesting things that one can do if one can take a specific fluctuation like a phonon or a plasmon or something that might be relevant for some phase transition, and parametrically enhancing its fluctuations and try to understand. This is, again, a very beautiful, I think, at least for me, way to act on for example, the thermodynamics of a phase transition away from equilibrium. If one can learn how to control these things properly, yes.
So are you really violating Kramer's chronic relation?
Come again?
So are you violating, let's say, the relation between the real and the imaginary?
I don't know the answer to this. I think so, because I think, although I'm not sure. So KK, of course, comes because of causality, and the question is whether away from equilibrium things are KK consistent. I don't know the answer to this.
But in experiments, we have measured the two at the same time.
See, we don't do KK. I mean, our experiments tend to be KK consistent, but then again, we measure things over a spectrum that is less than an octave, or a bit more than an octave. You see, so everything is KK consistent on these narrow spectra. However, because we measure both amplitude and phase of the field, we don't need to worry about KK. Because we extract epsilon, so our epsilon 1 and epsilon 2, or sigma 1 and sigma 2, are by definition correct. And they appear to be KK consistent over a very narrow spectrum, which doesn't mean anything. That's the answer to your, and I have not thought very deeply whether they should be KK consistent or not. Maybe Yannis, you have thoughts about this. You haven't thought very deeply either, good. Okay, how much time do I have? Okay, I can do two things. We can either talk, or I'm going to show you another thing, which is not super polished, but is a lot of fun too, and I can tell you that. What should I do? Fun thing? Okay, good.
Take questions at this time.
Come again?
Time for questions.
Okay, very good. So these are going to come back. Okay. The third thing, I mean, we've done many things, but the third thing that I really find really great, that at least because it's very amusing, again, in the spirit of this very complicated system, which has this nonlinear response that I can simulate with the sine phi and two equations that a student can do, is when we started looking at the response of the system close to the plasma frequency, but with very narrow frequency. So we want to look at the nonlinear optics of a very narrow, very spectrally pure field. This is very difficult because of technical reasons. This is something that nobody has ever done because it's very difficult. Because when you generate your terahertz pulses, for various reasons, you always generate them very broadband. However, if one can do this, we would like to understand how these nonlinear modes come in, and especially how they propagate in, and how is the nonlinear physics of now propagating wave. Everything I've told you up to now was by assuming that effectively there was no real propagation and everything was a standing wave over one skin depth. But of course, there's very beautiful, also spatially dependent physics. Okay? So the way you discuss how this light propagates through at least one junction of a superconductor is through the Sine-Gordon equation, okay? Which if you're a theorist, you know what it is. if you're an experimentalist, you often don't know what it is unless you're working on this problem. But let me walk you through this very nice equation where you have this second derivative in time and space, and then here you have a sine phase. Okay, and let's think about how all the electrostatic, magnetostatic, and electrodynamic properties of superconductors kind of come out of this in a very beautiful way, at least for me. I understand this is obvious for some people. If I apply a magnetic field, which means that the phase, if I apply a small magnetic field, which means that the phase will have no time dependence, because a static magnetic field only gives me a given flux, and the flux is equivalent to the phase. And if the field is small, which means that sine phi is about phi, what I have is an equation that defines the Meissner effect. And this is the Josephson penetration depth, which was in the Sine-Gordon equation. If I now decide, okay, let's not do this. Let's use a light field, which is weak. Then I can change the sign into a phi, and this gives me a linear wave equation. And this will describe the linear physics of the plasmons that come in. If I now instead decide that I'm going to make this cuprate very, very small, and so I get rid of the spatial dependency, okay? I get rid of this spatial dependency, but I retain the nonlinear nature of this. I get the Josephson effect, because now I have a second derivative equals to a sine, which gives me these oscillations. And if I now go back and take a strong magnetic field, so I take away the space dependence, sorry, I take away, yes, the time dependence, but I now give it a little bit of a kick. Remember, this is the assumption that HC2 is infinity, so something above HC1. What I get is a vortex lattice contained in these Josephson equations, because I have this second spatial derivative, which is equal to a sine. Okay, so this is, to me, is very satisfying, and at least at some level, it can describe an interesting nonlinear electrodynamics once I look at the Sine-Gordon equation in its full glory, which is this. Okay, the reason why this is very interesting in the context of the nonlinear plasmonics, or whatever we're saying, the Josephson plasmonics, is the following. So let's see, I can do some simulations. So a couple of people in my group figured out how to solve this in one dimension, and calculating exactly how you couple light in and how you couple light out. But here what I'm plotting is a plot of the phase. So the phase is encoded in the color as a function of time and space for frequencies that are and low fields that are above the plasma edge. And what I see is a plasma wave that propagates in, and this at a group velocity that is given by the slope. Okay, so far nothing special. If I go closer to here, where the nonlinearity starts to bite, what I get is that this thing breaks up into solitons. This is very similar to cubic nonlinearities in a piece of glass that you learn in laser physics, and you can form these solitons. But very beautifully, if you go just below the JPR, at 97% of the JPR, where in linear response there is no propagating mode, because remember, epsilon 1 is negative, so I have the wave is screened. What I get is that at zero field, I get, in fact, an evanescent wave, which evolves in time but doesn't evolve in space here. If I increase the field, I can look at this wave that because the sign starts to eat into the electrodynamics, I can increase my the penetration depth, and then once the field is above a certain intensity, a certain field strength, I get a propagating mode at frequencies below the plasma edge. This is not an electromagnetic mode, it's a solitonic mode that propagates in at a speed which depends on the strength of the field. Okay, and this is predicted by the code. And it's, the reason why this is very interesting is that this mode that propagates in, if you look at it, this is what we call a breather excitation. It's an excitation of the phase, which can be thought of as a pair of a vortex-antivortex pairs that oscillates, that propagates, and it oscillates in time at approximately the plasma frequency. So this comes out of the computer, so it has to be right. Okay? And so there's this. This is again my fine picture where this is the phase, and remember the magnetic field goes with the spatial derivative of the phase, which now I have a magnetic field that goes like so, and a magnetic field that goes like so, and these guys oscillate in space and they propagate in. So in principle, because of this nonlinear propagation, I can excite these modes. And again, whether these are useful or not, I don't know. But now what we've done is we've done experiments using a free electron laser. The beauty of free electron lasers is that they can generate very pure radiation. This is done in Dresden at an infrared free electron laser, where we could make strong fields and at various frequencies and look at the response. And again, what I'm going to plot now are pump probe experiments where I have this narrow field, and then I'm going to have a broadband pulse, and I'm going to plot the loss function as a function of time. I already told you about the loss function here, okay? And I'm going to go look for the vortex-antivortex pairs, okay? Or something that at least you'll see there's something that is, you know, if you're courageous, is consistent with it. Right, so this is now when the field is much higher. Now I plot the loss function as a function of time. These are experimental data. When the field is here, what you see is a redshift of the loss function, which is a redshift of the plasma edge. This is all trivially simulated. And I'm not even going to tell you why this is. Effectively, what happens is that the phase becomes a little bigger than 1, so the oscillator strength gets a little weaker. And as these modes are here, the plasma edge shifts a little bit to the red. All good, but at least this gives us some degree of confidence that our code can simulate something similar to what we see. Now, when we do the experiments at 0.97 of the plasma edge, what we see is clearly a very complicated excitation here at early times. And forget this, because this, you know, every time you measure it, this is different. But at long times, we see a very robust feature that looks like a Fano line shape. So the loss function broadens and forms this Fano line shape that then propagates for a long time, much longer than the time you would expect for an evanescent wave to go in and come out. So there seems to be, at high enough fields, a propagating mode when you come to this, and some highly nonlinear mess that is difficult to see. Now, if you take, so let's show you I'm going to show you now simulations. I'm going to take away this part, and I'll show you later why, because they don't look alike at all. And I'm going to show you that in both in the simulations and in the experiment, there's two Fano line shapes with a lifetime that is different. But then again, they're Fano line shapes that if you're in a good mood, you could decide that these look reasonably similar. Okay, also because you normally never saw something like this. Okay, remember, these are solutions of the Sine-Gordon equation with no free parameters. We just tell this, we just say, Sine-Gordon, calculate this, with and Sine-Gordon calculates. And this is an experiment done at the FEL, so at some level, maybe we should take joy in the fact that there is this Fano reshaping. And the reason why we believe that this Fano reshaping might be indicative of the excitation of such vortex-antivortex pairs comes from these considerations where you consider these vortex-antivortex pairs as being dark excitations, which are strongly coupled, however, to linear Josephson plasma waves, and hence the interference between this discrete level, this is a very fine level, and a broad level of the Josephson plasma wave might give you this dip. Okay? The reason why I haven't shown you all the dynamics is that, you know, you look at these two things and you really take a deep breath to say that they're similar, but you can only see this thing happening exactly at that frequency above a certain field, etc., etc. And the Sine-Gordon equation does a good job at simulating everything else away from this point where things are less nonlinear. So, but nevertheless, there's clearly this effect here, which might be indicative of the excitation of these vortices. And then there's a lot of other things. I'm just going to flash this. There's this work done by Yanis when he was working in my group, where he discussed the physics of Josephson plasmonics in cavities, actually in an array of coupled cavities. And he discussed how, because of the low frequencies of the Josephson plasmas, one could reach ultra-strong coupling between light and the superconducting order parameter in these. And this is something that might be useful if one tries to develop these or, for example, do things like laser cooling or try to do strong field manipulation of the order parameter in cavities. There's work we've done with the theorists where we have discussed that one can use parametric effect to cool the phase of these, and there's a lot of fun things. So I'm not going to say much more here because this is also not my work. This is a collaboration with Dieter Riacchi's group and Ludwig Mattei's group, where I just was bringing tea and sort of signing the paper. So that's I'm probably not in a position to say anything particularly deep about this. But starting from the Sine-Gordon equation, one can consider situations in which one might be able to cool superconducting fluctuations. That's it. That's all I wanted to tell you. I only told you one thing. I hope something came across. Thank you for your attention.